Assalamualaikum and a very good day everyone. My name is Nurul Aisyah binti ISHAH and my matrix number is BN20903. Today I will present about chapter 2, which is signal and noises. So have you ever experienced a phone call where the voice suddenly becomes unclear or radio signal filled with static noise? That problem happens because of noise in communication system. Yeah. So, electronic communication systems are the backbone of the modern technology. They enable mobile communication, television broadcasting, satellite links, and data network. However, no matter how advanced a system is, one major challenge always exists: noise, which degrades signal quality and limits system performance. That is why understanding signals and noise is extremely important for communication engineers. This project focuses on Chapter 2, which is Signal and Noise, a core topic in electronic communication system. The chapter is delivered through 3 integrated components: an educational video, lecture slide, and a comprehensive technical report. The main goal of this project is to strengthen our conceptual understanding, improve technical communication skills, encourage ethical use of AI tools, and develop effective teamwork, just like future engineers and educators in the digital era. Through this project, we aim to develop a strong understanding of signal and noise concept, explain theoretical principles clearly using engineering language, apply engineering knowledge to analyze noise effect on system performance, creative effective educational material support, such as videos and slides, use AI tools ethically as learning support, and improve teamwork presentation and report writing skills. Okay, let's begin with signal representation. A signal is a physical quantity that carries information from a transmitter to a receiver. In electronic communication system, signals are usually electrical or electromagnetic in nature. Signal can be represented in 2 main domains: the time domain and the frequency domain. In the time domain, the signal amplitude is shown as a function of time. This representation is useful for observing waveform shape, pulse duration, and transient behavior. Instruments like oscilloscope are commonly used to view time domain signals. In contrast, the frequency domain shows how the signal energy or power is distributed across different frequencies. This representation is essential for bandwidth analysis, modulation, filtering, and spectrum allocation. Frequency domain analysis is typically done using spectrum analyzer. Overall, frequency domain representation simplifies communication system analysis, especially when dealing with bandwidth-limited channels. Next, let's talk about noises. Noise is defined as any unwanted disturbance that interferes with the desired signal. It is random and unpredictable, making it one of the biggest limitations in communication system. Noise can be distort signal amplitude and waveform shape, reduce signal clarity and intelligibility, introduce errors in data transmission, and decrease the reliability of receiver circuit. Because of this effect, understanding noise behavior is essential for designing systems with better performance and reliability. Noise in communication system can be broadly classified into 2 main categories: uncorrelated noise, which exists independently of the signal, and correlated noise, which occurs only when a signal is present. This classification helps engineers identify noise sources and apply appropriate techniques to reduce their impact. In conclusion, a clear understanding of signal representation and noise behavior is crucial in electronic communication system. By mastering this concept, engineers can design a system that are more efficient, reliable, and resistant to interference. This project has not only strengthened our technical knowledge but also improved our communication teamwork and ethical use of AI tools.
Okay, now that we've covered the basic of signal and what noise is, let's dive into specific categories. We will start with uncorrelated noise. This type of noise is always present in a system whether or not a signal is actually being transmitted. It can be broken down into two main groups, which is external noise, which comes from outside the communication device, and internal noise, which is generated within the circuitry itself. Okay, let's look at the external source first. There are three primary types, which is atmospheric noise, also known as static electricity. These are natural disable like lightning. It mostly impulsive and usually doesn't affect frequency above 13 megahertz. And the second one, extraterrestrial noise. This comes from deep space. It includes solar noise from the sun, which peak every 11 years, and cosmic noise, which is the black body noise distributed throughout galaxies. And the last one, man-made noise. This is industrial noise caused by the things like electric motors or automobile emissions. You'll find this is most intense in busy metropolitan and industrial areas. Because noise is random, we can't just give a signal fixed value over time. Instead, we measure it using the root mean square RMS value. Okay, to find this, we first square the individual noise voltage measurement, then calculate the average mean of those squares, and finally take the square root of that average. Okay, as you can see in the example on the slide, if we take 10 different noise value, we sum their square to get 3.0325 V, and after that we find the mean, and then the square root gives us an RMS voltage of 0.5507 voltage. Okay, since thermal noise is the most critical factor for calculating how a system will perform, we use specific formulas to analyze it. We can calculate noise spectral density NO using NO equals to KT. To find the thermal noise power PN, we will use the formula PN equals to KTB, and if we need the noise voltage VN, we use the square root of 4KTBR. Beyond the main tree, there are other internal sources we must consider, which is generation recombination noise. This involves the random generation and recombination of carriers in semiconductors, which is treated similarly to short noise. And the second one, temperature fluctuation noise. This happens when heat is exchanged between a component and its environment through radiation or conduction. And the last one, flicker noise. This is interesting because its density increases as the frequency increases, making it inversely proportional to frequency.
Today I would like to present to you about noise and distortion in communication system and their impact on signal quality. First, correlated noise occur only when a signal is present and is mainly caused by a non-linear device such as amplifier. A common result in harmonic distortion when non-linear amplification produces harmonic and integer multiples of the input frequency. So if you see, third order harmonic distortion is especially harmful because it falls within the signal band. Overall, the distortion is measured using a total harmonic distortion THD, which is equivalent to the square root of V square plus V square plus a few more V squares over V1 times 100%. Another critical effect is intermodulation distortion or IMD, which occurs when multiple frequencies pass through non-linear devices, creating unwanted cross-product frequencies given by F equals to MF plus minus NF square. Next, the signal quality is measured using a signal to sound ratio SNR-dB equals to 20 log Vs over Vn, where higher SNR means a clearer signal. Noise distribution of a device is described by noise factor, which the formula is SNR in over the SNR output, and noise figure NF is equivalent to 10 log F. For multi-stage system, overall noise is calculated using the Friis formula, showing the first stage dominates performance. So that's all. Let's take a look at the example given. So in this example, we are given a telecommunication receiver with known input signal power, input noise power, thermal noise contribution, and power gain. So our task is to determine three things, which is the input SNR, output SNR, and noise figure of the receiver. So first step is to find out the input SNR. So to find the input SNR, we use the formula SNR in, which is equals to SI over NI. So by substituting the values we have, we will get the answer of 100. Next, we are going to change it in the form of dB. Using the formula 10 log 100, we get 20 dB. So the input SNR is 100 or 20 dB. Well, moving on to the next one, output SNR. So we know that the receiver has a power gain of 20 dB. Now converting it to a linear scale, AP 10 power 20 stroke 10, we get 100. So now we know that the receiver internal noise ND is 80 microwatt and the amplified input voice is equals to N out equivalents to ND plus AP and I. So substituting the values we have, we will be getting 1.8 times 10 to the power negative 4 watt. So now we use that value to find out our output signal power. So substituting the values, we will be getting 1 times 10 to the power negative 2 watt, and we can insert it inside our formula S over N. So with that, we will get the answer of 55.56. Now again, we have to convert it to dB. Thus, using the formula 10 log 55.56, we will be getting 17.45 dB. So moving on to the last question, where we have to find out the noise figure of the receiver. And the formula that we will be using in this is NF equals to 10 log SNR input over SNR output. So substituting the values we have, we will get the answer directly in dB form, which is 2.55. So that's all for this question. Thank you.